The third issue is Spider needs very precise delay calibration because we need delay in Spider, right? And this sentence means we know the delay tau is very high. A small error about the delay tau would be a big problem. Okay, but why is that? Let's assume the spectral phase to be measured is a simple quadratic function, coefficient c times omega squared. Then the spectral phase difference function should be a linear function of omega. Just substituting psi of omega by c omega squared. Psi of omega minus big omega equals c times omega minus big omega parentheses square. Calculation will give you this one. Okay, a linear function of omega. And then we also know the formula of interferogram is background spectrum plus 2 times p absolute value times cosine of tau omega plus spectral phase difference function. So now you just replace the red one by this linear function. In this specific case, then you can get this one. You see the linear function, the two linear terms are combined into the red one, right? Now the coefficient is tau minus 2c big omega, parentheses, times omega. And what does this formula mean? Okay. It means a residual delay tau 0. Okay, tau is here. Ideally, we need to calibrate delay tau in your setup and then making it 0 during data processing. If this term is truly 0, you got cosine of minus 2c big omega times small omega only. And your retrieval is supposed to give you accurate chirp parameter c. But if your delay calibration is inaccurate, so your delay tau is not totally canceled during data processing, say a residual delay tau 0 is left, and you see the status of tau 0 is the same as the status of c, a chirp rate. So whenever there is some error about your delay, it will be interpreted as residual chirp, the chirp that does not exist, right? And quantitatively, residual delay tau 0 will cause an extra quadratic spectral phase with a coefficient minus tau 0 over 2 big omega, and with quadratic function of omega. So that is a big problem because now your chirp rate is inaccurate. So your pulse shape will be inaccurate. Okay? Pulse shape in the time domain will be inaccurate. And this formula shows the problem will be more serious if you use a smaller spectral shear, big omega, right? The smaller the big omega, the larger the error coefficient. So when you try to push your spectral resolution by using a small spectral shear, you will exacerbate the delay calibration issue. Any small error about delay calibration will give rise to big error about your chirp rate measurement. Any question? 所以简单的说，就是我的系统里面那个 fixed delay tau，我要想办法把它量得很准，我才能够几乎把它 totally cancel 掉。然后 data processing 所抓出来的 chirp 才是真正的 test pulse 它的 chirp。如果你没有量得很准，这边有一点点残余量，它的地位就等同于你想量的 chirp rate， 所以你量到的 chirp rate 不是真正的 chirp rate， 是混合了 test pulse 的 chirp rate 以及 delay calibration 所残留的 error。OK， 而且这件事会随着你使用越小的 spectral shear 会越严重，它会放大你这个 error。好，那通常你会希望用一个小的 spectral shear， 以便我解析出来的 spectral phase function 它的解析度够好。可是你做这件事的时候，这个 delay calibration 的 requirement 就变得越来越严苛。Okay, so any question about spider? Okay, so maybe let's review the lesson. What is the pulse shape in the presence of cubic spectral phase? OK， 我看到有人的手指的微微的运动，我想是你知道，你有 cubic spectral phase， 你在 time domain 会出现 asymmetric oscillating tail。OK。Second question: What is a spectrogram, and why is it useful in measuring the temporal phase? What is spectrogram? A two-dimensional function with omega and tau two variables, right? So basically, you need a three-dimensional representation for a spectrogram. 那你如果觉得不是那么好想象，从这个词不太好想象，你就想五线谱，它就是一个 spectrogram. Different timing correspond to different spectrum. That is spectrogram. OK. 那为什么它有用？可以用来量 temporal phase. At different sampling time, you got different power spectrum, and you can record the peak frequency, right? Peak frequency represents the central frequency at this moment. And if you scan different moments, you can get the distribution of peak frequencies. Then you got instantaneous frequency function. After integration, you got temporal phase. Okay, so that's the basic logic. Third, what can we know and what can't we know from SHG frog? What can we know? Almost everything, except for some ambiguities. What ambiguities do SHG frog suffer from? They are essentially the same thing, but with different descriptions. In the time domain, it means time reversal ambiguity, right? E of t and E of minus t will create the same SHG frog trace, so you cannot tell the difference. In the frequency domain, the same thing means the sign of spectral phase is indistinguishable. Psi of omega and the minus psi of omega will correspond to the same SHG frog trace, so you cannot tell the difference. Okay? And why is frequency marginal function useful? Then you have to know what is frequency marginal function. There are two marginal functions. One is delay marginal function, the other is frequency marginal function. Each of them is obtained by one-dimensional integration of the spectrogram, right? It's a function of two variables. If you integrate with respect to delay, you got frequency marginal. If you integrate with respect to frequency, you got delay marginal. Okay? But why is it useful? 为什么有用? Mathematically, you can prove frequency marginal function, big M of omega equals what? The autoconvolution of which function? The function that you can easily measure experimentally. Okay, bonus question.还有人记得吗 ？Frequency marginal M of omega 是从 spectrogram 对 delay 做了积分后得来的。这个函数会等于什么函数？自己跟自己做 convolution。Which function? Symbol is not important. You can use any symbol, but what is the meaning of the function? I use I of omega in my notation, but what is the meaning of I of omega? Yes? Good, the power spectrum of signal pulse. And that's why it's useful. If it is related to some function that you cannot get it easily by instrument, it's useless. But I of omega, you can easily get I of omega by a spectrometer. So you can check whether the frog trace is accurate. Because if it is not accurate, the frequency marginal function will be different from autoconvolution of your power spectrum. Then you have to repeat the experiment instead of jumping into the data reversion. Okay. Fourth one, what are the differences between spectral interferometry and SPIDER? Let's think about the results. 他们各自得到了什么东西？不一样的东西。SI 得到什么 ？SPIDER 得到什么 ？SI gives you spectral phase difference function between signal and the reference. And the signal and the reference could be two independent functions, right? You just get the difference. You do not know the signal phase. You do not know the reference phase, but you know their difference. That is the function of spectral interferometry. How about SPIDER? What can you know from SPIDER measurement? This time it's not just the difference function between two unknown functions. What do you have? Yeah, 它是 shift. 那 shift 完做了积分，其实你就得到了 signal pulse 它的 spectral phase. Okay, not just difference, but itself. Okay, so 结果论来看，这得到不一样。这个只得到相位差，这是可以得到相位函数本身。OK， 那除了结果不一样啊，还有什么不一样？架构也不一样。好，那你就回想一下。For example, in spectral interferometry, there is no nonlinear optics. It's purely linear. You just need an interferometer and a spectrometer. That's it. But to implement SPIDER, you need nonlinear crystal, right? So that's the big difference. And there's some other things. Finally, why is delay calibration critical in SPIDER? That's the last issue I just analyzed. Whenever your delay calibration is subject to some error, it will be translated into the error in chirp rate measurement. Okay, and it's intolerable. The topic is about frog algorithms because we just introduced the frog. Okay, but in our lecture slides, I introduced a very simple algorithm, the iterative Fourier transform algorithm. And there are some problems there. I will show you. Then I will introduce two more advanced algorithms. the principal components generalized projection with acronym PCGP algorithm, and the least square generalized projection, acronym LSGP algorithm. And you will know why these two are useful in practice. Okay, and maybe in our second midterm exam, you can implement one of them, and you can tell the difference about performances between different algorithms. So let's start with what we have known, the iterative Fourier transform algorithm. This is a simple review, right? Initially, I just randomly choose a guess about electric field, A of t. With data constraint, I can know gate pulse by the signal pulse. For example, in SHG frog, G equals A, okay? Then you can perform A of t times G of t minus tau. You got gated signal, A sub sig of t and tau. Then Fourier transform, one-dimensional Fourier transform with respect to time variable. You got big A sub sig omega tau. Tau is intact, but the variable small t is transformed to variable omega. It's one-dimensional Fourier transform. And this is the gated spectrum. But in practice, we only measure the gated power spectrum, not gated complex spectrum. So all you have to do is replacing the magnitude of big A by square root of your measured frog trace. This is so-called data constraint, while leaving the phase component unchanged. So after that, you got updated gated spectrum, complex spectrum. Inverse Fourier transform, you got an updated gated signal in the time domain. Then the most important issue is from here to here. Previously, we used a very simple method, integration with respect to variable tau. You got something proportional to A of t, OK？ 所以这个演算法是用一个简单的积分做从这里更新到这里的动作。And that is the issue, OK? For the other two algorithms I'm going to introduce, everything else should be similar as iterative Fourier transform, except for here. Different algorithms will take different approaches to implement this updating. Okay. What are the advantages of this simple algorithm? It's very fast. It's easy to be implemented. Okay. However, frog error tends to stagnate if A of t is a multi-peak pulse. So that means sometimes this algorithm is good enough, but sometimes this algorithm has trouble. The frog error will not decrease with iteration. It just stays there. While if you stop there, the result is pretty poor. Okay, so that is the problem. And it happens especially when your signal pulse is multi-peak pulse. So that means better algorithm is needed when stagnation occurs. So if you look at, you monitor the frog error, if it does not decrease with time, maybe it's about the occasion to switch to other algorithms. Okay. So let me show you one example, single peak pulse. Okay. So this is your iterative frog trace. This is your target frog trace. So in the end, if they look similar, it's an indication that iteration works, converges, right? 它跑得很快，所以我再放一次。Sorry. 一开始不像，但是跑了没几次，它就跟右边很像。This is time domain result, and this is the frog error evolution, and you can see frog error continues to decrease with duration. So that means iterative Fourier transforms in this case. And the reconstructed pulse represented by blue crosses is very similar to target pulse represented by the green curve. So this means a single peak signal pulse has no problem. Okay. But in the second example, if your signal pulse has double peaks, you can see no matter how many times you try to iterate, the two frog traces will not look the same. The central one should be similar, but the two side ones look very differently, right? And in time domain, it means your algorithm tends to give you a pulse of 3 peaks instead of 2 peaks. Green one is the target. The blue one is what you have by iteration. Okay? And the last figure shows frog error stagnate, does not decrease anymore. So that means iterative Fourier transform algorithm does not work in this case. Now, I want to show you what is generalized projection. The concept is quite easy. Remember, we have two constraints, gate constraint and the data constraint, right? For each constraint, ellipse represents the set of electric fields functions satisfying gate constraint. So there are a lot of functions satisfying single gate constraint. Another set of functions satisfying the data constraint. And the closing point should be the solution, right? Satisfying both gate constraint and the data constraint. Supposedly only one function is there, and that is the solution, right? And what did we do? Usually we start with some initial guess. It's a random function, so it does not satisfy gate nor data constraint. It's a point somewhere outside the two ellipses. But this is only your initial condition. In our loop, we try to meet the gate constraint first, right? So it will project the initial point to some point on the rim of the first ellipse. Okay? Then, after Fourier transform, you try to enforce data constraint. So that means projection onto somewhere on the rim of the second ellipse. And the process continues, okay, to gate constraint to data constraint, gate constraint, data constraint. Hopefully, in the end, we will arrive at the solution. Okay. This is so-called the generalized projection. And the iterative Fourier transform algorithm has already implemented this idea. Okay. But instead of using a simple integral, some procedure is used in updating the signal pulse field from the gated field by minimizing the distance function. Okay. 我刚刚有说哈，我们的关键点是这里，这一步啊，从 gated pulse 要更新到signal pulse。过去只用一个积分，那现在用别的方法。这个别的方法的概念就是所谓的要最小化一个距离函数。啊 ，What is distance function? It's defined here. The double summation of absolute square of the difference between these two terms. The first one is the gated signal, The other is the gated signal predicted by the next round, next loop. OK， 这个就是那个回圈图左上角，你跑了一圈左上角 gated signal function of t tau。那这个是什么？这个就是我想知道下一步哈，所以 n 加一啊，第 n 加一个 loop， 它的 signal pulse 以及 gate pulse 各是多少？目前为止我还不知道这个是什么，而这个是已经知道的。那我就是要去找出一组 a n 加一跟 g n 加一的 new signal pulse and the new gate pulse such that the distance between these two-dimensional functions is minimized. 为什么要 minimize？ 这个差距越小，就代表我找出来的 new signal pulse, new gate pulse are closer to reality. If they are the right solution, supposedly distance function z is 0. Okay, so I just in every loop I try to optimize the updating. A simple integration does not minimize distance function. So that's why sometimes it does not work. But with this idea, we are supposed to speed up the convergence and arriving at better solution.